So Dr. Jan Rabaey received a PhD degree in Applied Sciences from the Catholic University Leuven, Belgium. In 1987, he joined the faculty of the Electrical Engineering and Computer Science Department of the University of California, Berkeley.
So can I start?
Yes, sir.
All right, good morning. It's a true pleasure for me to be with you this morning. I had wished I could be with you in person, but I guess this is the second best option, and we're going to have to stick to this video link. So my name is Jan Rabaey. I'm a faculty member at the University of California in Berkeley at the Electrical Engineering and Computer Science Department. Where I actually have been working on a set of topics related to sensor networks for quite a long time. Actually for probably more like 20 or 25 years. And it has been a thrill for me over the past couple of years to work closely with the University of the Philippines in Diliman as part of the PCARI project. It's been a true thrill, and I really have enjoyed the close collaboration we've had. So what I'm going to do today in this 10 minutes I have, I'm going to talk a little bit about the past, somewhat about the future, the present, where we're currently doing, and then looking forward to the future. What are the interesting things that you might see emerging? So let's get back a little bit in the past. Sensor networks kind of arose from, basically as an idea, somewhere in the mid-1990s. It was actually one of my colleagues, Chris Spiester, who came up with this term which is called smart dust, showing that if you look at technology evolution, it should be possible to build sensor nodes that are really small, that contain computing, sensing, communication, and energy storage, all in a volume that can go to very small dimension, potentially cubic millimeters. And that inspired us all to start working in this domain. It really required a lot of progress to be made on a broad range of topics. Low power design, energy harvesting, wireless networking, low power wireless radios, all those type of things had to be addressed for it to happen. But it sure did. But more importantly even was that the realization came together that if you have that technology available, the impact on society could be huge. The fact that you can actually start monitoring large energy networks, water networks, infrastructure, and so on and so forth, that you actually can truly build energy efficient homes through the deployment of those networks really got people very excited. And it was in the year 2000 approximately that in Berkeley we started a project which is called CITRIS, which was looking at the Center for Information Technology Research in support of society, using technology to help society make progress. It was a new idea at that time, because before that, all technology was primarily focused on productivity. So this all happened, but it kind of lingered in a limbo for a while. In the 2000s, a lot of things were happening, but you didn't really see any impact in the industrial community. And there's a couple of reasons for that. The main reason is that this technology is complex. It has many components. So for a person, let's say in looking at environmental friendly technologies, to deploy new applications, it was very complicated. They have to know everything from wireless networking, energy harvesting, battery replacement, networking, all those kind of things. And then you have to write your application on top of that. That's complicated. So that made it very hard for the general population to get access to these technologies. And that's really the realization that came to a number of people, I'd say in the late 2000s. That actually was worthwhile to think about, hey, if this technology is really going to happen, we're going to have networks of billions of wirelessly connected components, potentially trillions of connected components. And they form an interface between the real world and the cyber world. So you have this thing, but if you really want to make it happen, you have to have a set of software layers, basically virtualization layers, help you to differentiate between the hardware or isolate the hardware from the application development. So it's a lot easier for people to come up with new applications, deploy them, and execute them. And that really was the start of what we call the Swarm Lab in Berkeley, was this idea that indeed we're going to be surrounded by a swarm of devices of all kinds of natures, kind of put together in a semi-random way. And what we want to do is make them going to use in an effective way to solve real problems. And not basically creating dedicated network for a particular purpose, but I could create networks that are general purpose, like the internet, where everybody can access those net sensing capabilities and use them for their particular application. So overlay of applications. So that was basically the goal of the Swarm Lab, starting to develop these virtualization layers. And as a result of that, we had ideas like Swarm OS, an operating system to operate sensor networks, or the GDP, which you will be addressing in this workshop, the global data plane, which is an abstraction of a sensor network as basically a large database. So that's really what has happened, and this is the efforts we have been working on for the past years or so. So let me look a little bit forward into the future. I think the future of sensor networks is extremely bright. But actually the networks we're looking at today are somewhat limited in their capabilities. Today, most of the networks are basically monitoring network. They get information, access that information, and put it somewhere in a database that you can then basically access. The future really lies into networks that are completely closed loop, where you get the information, you process it, and you act on it. And you basically make things change as a result. A full control system, distributed control system. And this is not only going to include static devices, but will include a lot of mobile devices, dynamic devices, things like robots, self-driving cars, drones, you name it, are all part of that network. Collecting information, processing it, being smart about it, and then acting on it. Closed-loop systems. Now, to make that really happen, we have to make progress in many, many, many different areas. To be workable, these things have to be extremely robust. Right? It's scary. You have a self-driving car, you get information from a sensor, and you want to act on it, you want to drive around, you better make sure you do things in the right way, and you don't have any failures. So robustness is really important. What's also important is responsiveness. You cannot have data that arrives a day later. Sometimes you have to have milliseconds of response time before you can do anything. And it has to be secure. A lot of those networks are very critical, life critical in certain cases. So they have to be secure that nobody can hijack them. So security and privacy are real goals. But ultimately, I think for these things to be successful, they have to become intelligent. They have to learn from what they observe and adapt based on what they learn. So learning systems, artificial intelligence, and so on and so forth, both in a global way as well in a fully distributed way, are going to be very important. So I think this future is extremely interesting. It's a lot of things to be done. And I think it's great that we have a large community all over the world starting to address this particular problem. That's why I think this workshop you're having in this space is actually going to be very useful and very enlightening. So with that, I basically wish you all the best of success. I hope we can continue our close collaboration in the years to come. I must say, as I said before, I truly enjoyed it, and it really helped to make this into a more global community. Thank you.
Okay.
Any questions?
Any questions? Anyone? This is your only chance. Anyone? No question? Not one.
Well, don't hesitate to send me any question you may have by email. That's another option. Okay?
All right. Thank you very much, Dr. Rabaey.
All right, thank you. My pleasure. Again, enjoy the workshop.
Thank you. And so now we're going to move on to the introduction of the Sense project, an overview which will be presented by Sir Percival Mong Magpantay. Sir Mong graduated in UP Diliman, taking the Bachelor of Science in Electronics Communication and Engineering and the Master's in Electrical Engineering in 2001 and 2006 respectively. He is currently a PhD student here in Electrical Engineering and also an Assistant Professor of EEEI. His research interests include microcontrollers, sensors, and mobile robots, as well as the wireless internet. So I would like to call on Sir Mong for a brief overview of their sense project.
Good morning, everyone. It's been a while talking to a large number of people. I'll be presenting an overview of the recent project. So on behalf of our project leader, so basically the recent project is one of the many current projects collaborating with University of California, Berkeley. And we, in particular, are collaborating with Rabaey and Dr. Paul Wright. And we have been visiting the university for around 2 years, for about 1 month for each visit for collaboration. So basically, as what Dr. Rabaey explained earlier, so we are looking at the future of many sensors or connected networks. Okay, so we are also in this project we are also looking in that direction, wherein we envision a large number of sensor nodes to be connected everywhere. Okay, so we are aiming at large-scale, heterogeneous, and especially when sensors or sensor networks are getting larger, okay, they have to be resilient. So in this particular project, we just aim to at least look at electric power monitoring control, building monitoring, and environmental monitoring. And to start working on that, we developed a research platform. So this basically the hardware and software component of the project to enable us to go into that direction. Okay, so for our part, the EEE part, okay, we are developing the sensor nodes, energy harvesting, network resiliency, and some other test application for testing our platform. And then for the UCB, we are using their global data plane and the swarm boxes, which are connected together. And then for the energy part, okay, we are working with the UCB AME for printable capacitors and printable solar cells. So those are mostly futuristic research areas. Okay, so mainly the EEEI Microelectronics Laboratory is in full support of this project. So here are the faculty in charge. Okay, so if you are prospective students, okay, you may approach them, okay, for your MS or PhD graduate studies. And for the team that actually worked on this project, so here they are. Okay, so as I have introduced earlier, okay, we are looking at a very large scale sensor networks deployment in the future. Okay, so we want to work on them right now so that we are prepared, okay, when that happens. Okay, so basically, our project is, this is the basic overview of the recent project. So we are building an open infrastructure for different sensor networks to connect at, and then their data can be accessible to every sensor networks and every application, everyone or every application developers that want to use those data. Okay? So why do we want to do that? The sensor networks or wireless sensor networks in general is actually rapidly being deployed in different applications, okay? Medical, environmental, industrial, etc. So there are many sensor networks deployments around. Okay? So the problem with that is that those different sensor networks use different technologies to store their data, access their data, and then for those different sensor networks, they are only accessible to their particular application. So, for example, we deploy some sensors for this room or temperature monitoring. One project did that, and then next project, let's say next sem, other projects want to investigate the lighting conditions. Okay, so if there are two projects working on that, then they are not related in general, so they have different advisors, for example. Then those two sensor networks will be what do you call this? They are separated and they will not be connected. Then the data for those two types of sensor networks will not be linked. Okay? So, but if those temperature data is related to the, let's say, the lighting conditions, okay, so what can we do about it? So this is one of the goals of this project. So even though we have deployed some sensor networks in the past, can we use them now or in the future so that we can build additional information, okay, on top of those sensor networks? Okay. So basically, we are building a platform so that those paths or those sensor networks can be put in our platform, or future platforms can be connected to our platform, and then some other application developers can develop their own applications to use those data from the different sensor networks, and then they can actually build a virtual, let's say, virtual sensors, okay, using those different data. So basically, this is block diagram. Nakita niyo ba yung nakita? Sorry, gagalaw na lang. Sorry. Okay, so example, these are the two layers. So this is the application layer, and then this is the mostly the hardware part layer. So to connect those two, we have this what we call the Resense Global Data Plane. So the Resense Global Data Plane is custom, or is basically the global data plane developed by Swan Lab. Okay, then we just tailored it to fit our project for that. Okay, so if you want to develop these applications above, okay, and we are using different sensor networks. So in the past, if there are air quality monitoring network, okay, or sensors, okay, deployed, then there's a particular air quality application for that. Okay, and then for water quality monitoring, and there's a water quality monitoring application for that. But then, if we want to use, if we want to create another application layer that want to use the data for the air quality and then the water quality, okay? So what we want is that for this global data plane, okay, using this global data plane, we can access all those data, okay, and develop a new application for that. Okay? So that's basically what we want to create. Okay? Build a platform, okay, that is accessible to different application developers. Okay? And also, to go to billions of nodes, we cannot deploy billions of nodes at once. Okay? So we will build them essentially incrementally. So that's why we think that this approach is one correct approach to go in this direction. So, some details on the EPP GDP system architecture. This will be essentially discussed to you later. Okay, so this is just an overview of the GDP that we are using. So basically, we are building this custom channel architecture, okay, which is the link between the application layer and the sensor network layer. Okay. And this thing here is somewhat a central application that manages all the communications from the hardware sensor network to the software application network, so, and vice versa. So, more details on the directions of the information. So, if we are building an application, this is the layer, okay? We are creating different channels, okay? So, that's why it is the custom channel architecture. Okay. So for different applications, you can create, let's say, a number of channel commands or command channels, and then a number of channels for, let's say, data and requested data. Okay. So one of the things that, since we want to go to the direction that we will have a resilient network in the future, and the resiliency application essentially can be done in the node level or in the network level, etc. Okay, so since what we're thinking is that we are building incrementally the large-scale network. Okay, so what we can do is to prepare for the resiliency of the network is that we create what we call a resiliency service. Okay, so what it does is that we are monitoring the network traffic of our sensor networks, okay, by deploying what we call steeper networks. So essentially, kung hackers kayo, okay, so basically parang we are listening to our wireless networks, okay, via steepers. Okay, so parang passive at siya, passive network monitoring. Okay, so we are deploying a number of steeper networks. Okay, and it is essentially a different network from our monitoring sensor networks. So we estimate our network data from this steeper network, and then this also goes to the global data plane. So essentially, it is one sensor network. Okay. And in the future, you can actually correlate the network data to sensor data, let's say especially the temperature data or the humidity data. Does this affect essentially the nodes? Is the power consumption related to increasing temperature, increasing humidity, etc. Okay? So all those can be done using our global data plane framework. Okay, some details. So to enable the resiliency, so basically what we try to do is to control the operation of the nodes. Okay, so by using that, we create interlayer application, what we call the resiliency app, which controls the nodes, okay, from lower levels. Okay, so essentially we can control the sleep of the nodes, or if we can disable the nodes, okay, or we can enable the time where when the node will be awake each other. And to test all those, we created a visualization application. So this will be demonstrated to you later. Okay, so to build our platform, we are working in this laboratory, room 203 in Building 1, license laboratory. Okay, so for building the nodes, we are using 3D printers and laser printers, laser cutters, sorry, to create our sensor nodes. Okay, so for the first version of the node, we used DG XB modules for the RF communication. Then we have power management, and we use some lithium-ion batteries. And for energy harvester, we just use off-the-shelf solar components. We'll just discuss this later. Okay, so we use sensors, power line for current and some voltage, and then we use battery and internal transfer temperature for battery for load health, and then for the external environment, we use temperature and humidity. So these are some example of deployment in the power panel of the building one. Okay. Now the second version is on the way. Okay, so it uses an Atmel microcontroller. Okay, it is much low energy than the previous one. Okay, so that's why we want to use it as our next node platform. Okay, so I mentioned earlier that we are working with AME for the energy harvesting part of the project. So what you can see here are the actual printable solar cells. Okay, this is a prototype made from lab in Berkeley. Okay, and use them to power our sample node version 2. Okay, so this is a printable version. So using the solar cell and a supercapacitor, this node can be powered with sunlight. Okay, so you can charge it for about minutes or around 5-10 minutes, and then you can operate it for about same number of hours. Continuous work here. So gusto nyo, if we want to prolong the battery or the energy of the node, then you can essentially cycle the on and off power of the node. Okay, and one of the components of the project is essentially the power management. Okay, and to do that, we are also developing a power management integrated circuit. Okay, wherein it can get power sources from different energy harvesters. Okay, so from AC energy harvesters or DC energy harvesters, and then we can have provisions, okay, on how energy is being transferred from the energy harvesters to the battery to the sensor node and vice versa. Okay, you basically have provisions on how you will use the energy that you get from different, in this case from two energy harvesters. Okay, can you manage the energy if you see that one energy harvester has more energy, okay, etc. That is just some details of that. This is just sample deployment. Okay, so right now we have 50 plus nodes in building 1. Okay, and deployment is still ongoing to approach 100 nodes. Okay, in 1 or 2 weeks. Okay. So as I have said, we are deploying in building 1. Okay, and we are visiting Berkeley at least or once or twice a year during the project. This is our last design workshop. Okay. So that's where we experiment on their printable solar cells. Okay, so the planned next phase should there be funding. Okay, so we want to expand the platform from one building to the whole university campus. Okay, so essentially the academic oval. Okay, and we are focusing on since it is an outside deployment. Okay, some work on resiliency in the node level, okay, how to go against the environment outside, okay. Then also on machine learning and virtualization of sensors. Okay. So more on artificial intelligence in this next phase. So this is the planned deployment.